Okay, I wanted to go over one problem, which was number 50 from chapter 8. It covers basically all the different things that you need to know at this point about finding the solids when you're revolving a shape around different axes or different lines. Okay, it was one that Uzi, or Lil Uzi Vert, as I like to call him, brought to my attention. It's a good problem. And um, I think if you can get through all these, then you have the basics that you need for the AP test. So first of all, you're often going to be given a bunch of different lines, and those lines are going to come together to give you a shape. First part of the process on these problems is just recognizing what the shape is. So in this case, we're talking about that shape. That's the intersection of those three lines. And then we're talking about 5 different scenarios where you're revolving it around a different axis. The first one is revolving it around the x-axis. Okay, so notice what happens when I revolve this thing around the x-axis. The key to doing this is to picture what one of the cross sections will look like. Okay, if I look at that one x star right there, I'm going to get a cross section that looks like a washer or a donut. Okay, what's a washer or a donut? It's a shape that has two different, like two circles. I think that's called a torus technically. But it has two circles. It has a big radius and it has a little radius. What gives me the torus is the fact that there was space in between the shape that's highlighted and the axis that I'm revolving it around. So anytime that there's an empty space, that dead space in between the shape and the axis that you're revolving it around is going to give you empty spaces, and that's what creates the hole of the washer. And so you need to take into the account the formula for the area of a washer is r squared pi or minus r squared pi. And I know I wrote those in the opposite order that you normally see them in, but you can factor out the pi there, and it's going to be pi times r squared minus r squared. So that informs the formula you need anytime that you're using washers. And what you just have to do is figure out what's the big circle and what's the little circle. So in this case, the big circle, it's going to be an integral, right? The big circle is going to be big R. So that big circle in this case is just 5. No matter for all x's, it's going to be 5 squared minus the inside circle is going to be 2 to the x plus 1 squared dx. And I need a pi, and I need to know that x is going between 0 and 2. That point right there is 2. Okay? So now what happens in B? In B, we're not rotating around the x-axis. Now we're rotating around the y-axis. So what happens now? Well, now there's no space in between the highlighted section and the axis that I'm rotating it around. So it's instead of a washer, it's going to be just a disk. A disk is easier. That's just your formula for a circle, pi r squared. However, since we changed our orientation, we need to take this equation, y is equal to 2 to the x plus 1, and I need to make it so that x is a function of y rather than y as a function of x. So I think I can get 2 to the x is equal to y minus 1. I could take the natural log of both sides. And what that allows me to do is bring the exponent down and then divide by the natural log of 1. And I get natural log of y minus 1 over natural log of 2. And so the reason I did it that instead of taking log base 2 of both sides, it's just that I don't have a log base 2 in my calculator. So leaving it in natural logs is easier. Now I'm going to go the integral from 2 to 5. Y goes from 2 to 5 of natural log of y minus 1 over natural log of 2 squared, and I need the pi on the outside of it. Boom. So that's disks. That's with respect to y. What you can a thing you can keep in mind is that if your axis is horizontal, you want it to look like y as a function of x. If your axis is vertical, then you want it to look like x is a function of y. Those rules, as long as you're using discs or washers, those rules will not change. If you're using shells, which I'm not going to teach you in this video, but right after this video, then that changes something. So part C, now it says y is equal to 5. Okay, y is equal to 5 is this line right here. And so what happens when you get this, you get disks. But if you think of what's the radius of one of these disks, it's not as easy as just squaring the function. In fact, what's the radius of this? This is 5 minus 2 to the x plus 1. It's 5 minus that whole thing. So when you have an axis that's above it, like above the shape, you're usually going to want to do this, where I'm going to go from x goes from 0 to 2, and it's 5 minus 2 to the x plus 1 dx, and that whole thing is squared. And I got to multiply it by the pi. Or I suppose I could call this pi times the integral from 0 to 2 of 4 minus 2 to the x squared dx. When I do d, these are just becoming different variations of other ones. But when I do d, what you should notice is that now it's x is equal to negative 1. Okay, so I want pi times the integral as x goes from, y goes from 2 to 5 of natural log of y minus 1 divided by the natural log of 2 plus 1 squared dy. Okay, and so I'm plussing 1 to compensate for the fact that I'm plussing 1 to compensate for the fact that the big circle is 1 off from the x-axis. However, the way I just set this up was as if it were discs, but this is in fact washers. So what I would need to do in this one is subtract 1, because there's an inside radius of 1 dy. And now for the last one, which is y is equal to negative 2, y is equal to negative 2, clean this stuff up, is down here. It's off the charts, but we can still picture it. What's going to happen? It's going to be a washer. The big radius, what's the big radius going to be? Well, it's going to be 5 plus 2, because the line is at 5, but on every one it's plus 2, so it's going to be 7 squared. What's the little radius going to be? It's going to be 2 to the x plus 1 plus 2, or 2 to the x plus 1 plus 3 squared dx. X goes from 0 to 2. I need a pi, and that would be an example of basically every different type of one of these problems that they could throw at you. And if you can read my chicken scratch, then you have the answers to all those questions.